So the first stop in our exploration of how to prove the two figures are congruent is going to start with some postulates for proving that triangles are congruent. And the reason that we're starting with triangles, as we will in several other explorations later on in the course too, is that triangles are relatively simple. They have three sides, they have three angles, and so in order to show that all of the corresponding pieces of two triangles are congruent, we actually need a relatively small amount of information. The simplicity of a triangle makes it ideal for showing that two triangles are congruent to one another. And so, basically, how do we show that two triangles are congruent? Well, if we can show that enough parts of them are congruent and in the right orientation, then the triangles must be congruent too. The more sides you add, the more angles you add, the more complex it becomes to show that two figures are actually congruent. So the first of those postulates is something that we call the side-side-side postulate, which says that if three sides of one triangle are congruent to three sides of another triangle, then the triangles must be congruent. Or said another way, if you know that a triangle is created out of a set of sides that have three particular lengths, there is only one way for that triangle to be created, and there are no other triangles there. So first, go ahead, pause the video, copy down the side-side-side postulate. It will probably also be helpful for you to copy down the diagrams at the bottom of the screen, and then come back when you're ready to see an example of a proof using side-side-side that shows the two triangles are congruent. So let's take a look at what this actually looks like. Anytime we're using any of these three congruence postulates, our goal is to show that the corresponding parts of the postulate that we're using are congruent. So if we're going to use side-side-side, the things that we need to do in our proof are say that there are three sets of congruent sides and show that as a part of the proof. So here, if we're given that triangle ABC is isosceles and that D is the midpoint of AC, we can prove that triangle ABD is congruent to triangle CBD. So how are we going to do that? Well, let's split into our statement and reason columns here. What we are given is that triangle ABC is isosceles and D is the midpoint of AC. To save space, I'm not going to put that in the proof, but you would give exactly that there. Well, if we know that triangle ABC is isosceles, then we know that per the diagram, AB is congruent to BC, because that's part of the definition of an isosceles triangle. Great, that is one set of sides. Side one, check. Next, we know that D is the midpoint of AC, so we know that AD as a segment is congruent to DC, because that's part of the definition of midpoint. Cool, so now we have one side with the set of sides with the isosceles triangle, another set of sides with the midpoint, check. And now, BD as a segment that is shared by ABD and CBD is something that we call a shared side. So BD is congruent to itself because of the reflexive property of congruence. But because it's a shared side, it counts in both triangles. We still need to say that BD is congruent to itself, because that is the third side. Our three steps of showing that 1, 2, 3 sets of sides between the two triangles are congruent is what we need to do every time we want to prove something with side-side-side. The postulate name tells us what needs to come before the critical step here, which is great. So then, triangle ABD is congruent to triangle CBD, and that is by side-side-side. So that's the way we're going to follow for every proof where we show triangles are congruent. It's going to be whatever components we need to show that triangles are congruent using a particular postulate. We have to have a step for each of those that says, in this case, 1, 2, 3 sets of sides are congruent, and therefore the two triangles are congruent. Now, the next way that we can prove two triangles are congruent, because we may not know always that 3 sets of sides are congruent, is something we call side angle side, or SAS. Importantly, if two sides and the included angle of one triangle, that is the angle that is created using those two sides, the sides are the edges of that angle. if those two sides and the included angle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. Again, congruence doesn't matter as far as orientation on the page is concerned. So triangle EFG and triangle HJI are congruent even though one is flipped vertically from the other. So go ahead, pause the video, copy this entire slide down, come back when you're ready to see an example proof using SAS. So again, the most important thing here is that the angle is included. That really is critical. When we say side angle side and use the names of the postulates, that means wherever there is an angle or a side relative to the other type of object, an angle between two sides in SAS means the angle between the two sides in the triangle, not an angle off somewhere else. So let's go ahead and look at this. In this case, we know that E is the midpoint of MJ and that TE is perpendicular to MJ. So we want to prove that triangle MET and triangle JET are congruent, and we're going to use this using side angle side. So again, starting with our statements and our reasons, is our job to show a side, the included angle, and another side are congruent to each other in the two triangles to use SAS. Well, the first thing that we know is that E is the midpoint of MJ. Again, I'm not going to put it in the proof for the sake of saving space, but the given should be the first line of every proof. If E is the midpoint of MJ, then ME is congruent to EJ because that is the definition of midpoint. I'm going to abbreviate that MP. Cool. ME, EJ, good. Side. There's our first side. Now we could take our next step and talk about the other side. We don't have to show them in the order of side, angle, side, but their orientation in the triangles has to be this particular way. So let's just go ahead and do that next anyway. So we know that TE is perpendicular to MJ, which means that angle MET and angle JET are right angles. That is part of the definition of perpendicular, and because they're right angles, that means they are congruent. Notice we have to use all three letters here because there are multiple angles around E. And why are they congruent? Well, because they're both 90 degrees, and that's because all right angles are congruent. Great. So now we have a side, an angle, and now if we're going to use side angle side, then the other segment that is used to create angles MET and JET need to be congruent to each other, and then we have side angle side. Well, the other side in both triangles is side ET, which is congruent to itself because of the reflexive property. Which we reminded ourselves of in the last proof using SSS. And then finally, now we have side angle side, and we can say what we've wanted to since the beginning, which is that triangle, get a different color there, triangle MET is congruent to triangle JET because of SAS. Again, we need side, angle, and side proven to be congruent with the angle included to use SAS. Every proof using SAS must include those three steps before you can go straight to the SAS postulate and say that the triangles are congruent. The last way that we can prove triangles congruent that we're going to see in this video is ASA, or angle side angle. This is if two angles and the included side of one triangle are congruent to two angles and the included side of another triangle, then the triangles are congruent. Again, the key word here being included. That side has to be shared by the two angles that we say are congruent, or we do not have the ASA angle side angle postulate. Included is critical. So go ahead, pause the video, copy down this postulate as well as the entire slide, come back when you're ready to see one more proof and wrap up the video. So here we go, one last proof with ASA. In this case, we're given that E is the midpoint of AD and that AP is parallel to OD. We want to show that triangle APE is congruent to triangle DOE. Now, if you want to go ahead and attempt this proof on your own before you see it done in the video, please pause the video and try it on your own. If you can see how we're going to do this here, it helps a little bit that we know we're going to use the ASA postulate, so we're just looking for some congruent angles and some congruent sides. But if you'd like to just let the video roll and see it, that is totally fine too. So if you're going to pause it, do that now. If not, just wait here for a second or two and we'll continue. So again, with the ASA postulate, what we want is an angle, a side, and an angle to be congruent so that the side is included between the two angles. Well, in our givens, which would always be the first step, even though we're not including it there for space reasons, we know that E is the midpoint of AD. That means that AE is congruent to ED, and that is by the definition of midpoint. So we have that in the diagram. Great, we have the side. Now it's our job to show that the two angles on either end of that segment are congruent. So now we're looking at angle PAE and ODE, as well as PEA and OED. So it's easy to see that PEA and OED are going to be congruent because they are vertical angles made by intersecting segments AD and OP. So that is angle PEA congruent to angle OED. Because of the vertical angles theorem, vertical angles are congruent. Great, that is one angle that we want. And now on the other side, we have these angles where our congruent segments intersect with parallel lines. Well, that's really nice for us because we know something about parallel lines and transversals that intersect them. And as it turns out, angle EAP and angle ODE are alternate interior angles on those parallel lines using the transversal AD. So if we extended them a little bit, we could see that they are alternate interior angles. Therefore, angle PAE is congruent to angle ODE because of the alternate interior angles theorem. And there we go. An angle, a side, and an angle with a side included are congruent between these two triangles, and that gives us what we wanted to show all along, which is that triangle APE is congruent to triangle DOEO, not U, and that is by the angle side angle postulate. So the key things to take away from the video is that there are three primary ways that we are learning now to show the triangles are congruent. There are some more, and we're going to learn them later, but the three that we learn in this video are the side-side-side postulate, the side-angle-side postulate, and the angle-side-angle postulate. And anytime we have a proof, including any of those where we want to show the triangles are congruent, it is our job to show that those three components are congruent between the two triangles. Then we can use the postulate. But we must have the three steps that show that the side, 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 the side included angle and side, or angle included side and angle are congruent. Otherwise, we can't use them.